Dear participants of the Roboter tutorial at the ICRA2014 in Hong Kong, my name is Krupke. I'm from the University of Hamburg. I study computer science at the Department of Informatics, and currently I work as a student assistant at the TAMS group. Unfortunately, I can't be with you in person because I have to take care of my final exams. Because of a change of date of one of these exams, it was not possible to come. Yeah, I want to present to you our design of a modular robot that consists mostly of standard components and printable housing parts. The advantage of using printable housing designs is that you can integrate everything you need and as you need. For instance, we integrated slots where perfectly fit our control boards. And if you want to change something, then you can change it in your 3D model and print a new one. One printout of a housing part is very, very cheap, and so you don't have to take care of small changes. And it's also quite fast. It's available to you. You can directly check your idea after changing them. Our main design concept was to create it with as few cost as possible, because the main idea was only to build something for myself. And so it had to be affordable for students. Since my colleague Florence Wasserfall was working on slicing algorithms of FDM 3D printers, I had the idea to start to design a housing for a modular robot, because the general structure of these housings is very simple, and so I tried to design something with a CAD program. The clue is that if you design your housings on your own, and you can easily change it to adapt new components. One of the main parts of the housing holds, for example, the control board. It fits perfectly into some slots prepared for it, and in this way we don't need any further mounting devices. Of course, if you change the control board, you could also change the design of the slots designed for it. We decided to use magnetic connections at the interfaces of the robot. Neodymium magnets are quite powerful. You can put hardly weight on it, and it's no problem for the robot to compensate this. So we designed something that is manually reconfigurable, and you don't have to take care of how to disassemble it or reconfiguring. This proceeds in the software, because we created an autonomously detection of the topology of the whole robot. But that I'll tell you later in detail. One of the most important features is that you can use the 3D models that you need for printing with the 3D printer in a simulation. My diploma thesis was related to modular robot simulation and locomotion generation, and especially the optimization of locomotion control parameters. And we implemented this robot as a completely distributed system. Every module has its own microcontroller, so also distributed algorithms could be used in this way, like CPGs for instance. Despite of the features, it's very low cost. One module costs around $20 and includes everything, the material needed for the printing, the electronic parts, and also the screws and wires. As a demonstration of the robot, we prepared a small video that you can see some of its current functionality. Once you have finished your design of the robot, you can reuse the housing 3D files for a simulation. The simulation system allows for optimizing the locomotion modes. Over the time, we created several versions of the housing to react on design failures. If you have a look at the connection interface, then you can see that it is composed of two squares, the outer and the inner square. The outer square is for the power supply, which builds a kind of bus. The inner square is for the communication lines. To allow for changing the relative orientation of neighbored modules, we had to offer the connections in a redundant style. One very difficult part was to connect the wires at the magnets. Of course, we can't use heat, and we did not have some kind of conductive glue. So we had to think about something more tricky. As you can see in the slide, there's a hole for the magnet that inhibits the magnet to be pushed totally into the plastic material. Then there's a slot that fits for a nut. Into the nut you can put a screw, and between the head of the screw and the nut you can place some wiring. Cable clips are the appropriate choice to connect cables to the cable clip, and the cable clip in the hole of this the hole of the cable clip is used to put the screw inside, and then you can screw it in the nut, and in this way you get a kind of a plug. Here you can see all of the components, or mostly all of the components we used to assemble one robot. We have three different levels of control. The inter-module communication is used for some automatic communication between the modules. Autonomously, the topology is detected all the time the robot is running, and it also recognizes changes by sending heartbeat signals to the neighbors, and if one neighbor doesn't answer anymore, then we know it's not connected, and because we have a point-to-point connection and not a bus, we know that also its siblings are not connected anymore. So we can change the configuration or the stored topology in the master module according to this. And the module that lost connection tries again to connect if it still works. So if we had only if we only had a small disturbance, then it's not a problem, because we can establish the connection again. Low-level commands are used to create locomotion. There are some commands like set angle that is used to move the servo motor of a single module. This is the basis for locomotion generation of the master module, but also of some external controllers or some local controllers that can be added in a payload slot of one module. It allows for implementing several control locomotion algorithms. Then the high-level control can be used to start some stored procedures in a master or maybe a local controller. Since communication is done with a master controller via interface of USB or Bluetooth, you can bootstrap some new locomotion modes by sending high-level commands. Here you can see the summary of a robot interface. From outside, which can be a local controller or a remote controller, you have access to the high-level interface, but also to the low-level interface. So you don't need to use the stored procedures. You can also send some Printable commands. These are transduced into the inter-module communication, which is based on communication of chars. Yeah, what we've done so far is to create an experimental low-cost modular robot platform in hardware and software. We designed the housings, created the software, which is based on some Arduino libraries. We realized a magnetic connection interface for power supply and communication. And the communication protocol was based on a UART, which was a kind of experimental feature. Maybe next time we could utilize the ICRA2014 protocol to use a real bus, because it would be helpful when using many more modules, because the point-to-point interface has the drawback to have a high load on the bus if you use many modules. As future work, we are eager to know how the distributed locomotion generation works, because this would dramatically reduce load on the bus, and so it should perform very well on a point-to-point based interface. Then we think about how to integrate sensors, or which sensors could be most useful or most interesting to integrate, because there are also a lot of low-cost sensor breakout boards out there. For instance, IMUs or simple switches for checking if contact to the ground is established. And another thing would be to create other modules, to create some heterogeneous structures. For instance, some rotating module that allows for dynamically, autonomously changing the orientation from pitching to yawing without manual reconfiguration. Yeah, that's it. Thank you very much for listening to my talk, and I'm very eager to know if you have questions. Then just send me a mail and I'll do my best to answer